back and forth.
Oh, really? It could be my adapter. I went for the, it's funny, the $3 adapter for HDMI to USB-C works great. The like $25 Apple one, it's like constantly like flashing the screen.
Good.
So pays to be frugal at times, I guess. Energy and variational methods are needed for other elements. Guess I could get this a little bigger. In this case, right, for example, plates are a big one, as you'll find. It would just not possible. Okay? For now, we're going to consider linear problems. Right, for linear problems, we're going to say that the material doesn't, or materials won't crush or yield. We're also going to make the assumption that our deformations are small enough that we can develop equilibrium equations considering only the undeformed geometry. Okay, so deformations. Welcome, Emily. Undeformed geometry. Which simplifies things a lot, right? You get this kind of P delta effect if our deformations get large enough to where our deformations in our element start contributing to changes in stress and strain and forces, right? So we're going to look at a bar element. As I mentioned, we're going to consider linear elastic. Okay. That's our constitutive assumption. Our stress and strain vary linearly. We're going to have some sort of length L. We're going to have some sort of modulus E, which is going to be constant, and some area A, also constant. And we have this bar element, right? We've seen this a few times now. Has some distance, right? Some length L attributed to it. We're going to have some sort of deformation, right? Displacement at our two nodes. Right, nodal degrees of freedom, only in the axial direction of our bar. We're going to have deformation 1 and deformation 2 associated with node 1 and node 2. Right, this would be node 1. This is node 2. Okay. So we're going to develop our stiffness equations. Sutton, welcome. If I could lock that door, I would. You know that? Yep. 9:09. What the fuck?
Cold outside. Slow drivers.
None of those are real excuses. You know that, right?
Working hard.
Right? It's what'd you say, Sutton?
I was at work.
Oh, so now you're saying work's more important than me. Huh? Where do you work?
TDH.
Oh yeah, you said that. Did Scott Maheron keep you or something?
Yeah.
Tell him I'll never buy him a beer again.
Yeah.
So we need to figure out what's going on internally, right? Well, one approach to do this would be an equilibrium approach, where we would essentially cut our element at some distance from our first nodal point, right? We have some force 1 acting at node 1. And within our cross-section, we would have some sort of stress times area, right? Or force. So sigma A. If we sum the forces, we get F1 plus stress times A, right? If we use our constitutive relationship, assuming linear elastic, we get to use Hooke's law. Stress now becomes E epsilon times A, where epsilon, right, is our change in length over the original length. Well, our change in length can be related back to our change in our deformation of our nodal points, right? U2 minus U1. Well, if epsilon is U2 minus U1 over L, we end up getting this equilibrium equation that then becomes EA over L times U2 minus U1. Rearrange it one last time. F1 now becomes EA over L U1 minus U2. Call that equation 1. If we looked at an overall free body diagram, right, back up to the top, we know that F2, right, has to be negative F1, right? If F1's acting to the right, F2's got to act to the left. So they're opposite one another. You can say F2 is negative F1. So we get EA over L, U2 minus U1 is F2. Right, I just switched the signs I did. Instead of U1 minus U2. U2, it's U2 minus U1. So these two equations, right, 1 and 2, really provide a system of equations, right, with respect to forces, material properties, right, geometric properties of our element, and deformations. So we can rewrite this for convenience in matrix form, and this is where, well, I guess I'll rewrite these equations, right? So we have AE over L, U1 minus U2 equals F1. And we have AE over L, U2 minus U1 equals F2, right? Well, we're trying to come up with a stiffness matrix, right? That's the overall goal, is to understand what is going on, or what we would call our characteristic matrix. Right? You guys have probably seen this form, right? What is the form of this? What's the form of a spring, right? The force in a spring is, you guys took dynamics? Stiffness times deflection, right? What we would call our K D equals F, right? That's what we're really trying to go for. What's that?
Nobody calls it D.
That's how I call it. Well, Cook calls it D, and so I'm trying to follow Cook.
Okay. Little F.
And little f. All right? Say the big F for you. What is it normally?
I think it was KX.
Oh, okay. Yeah.
Big F.
I guess so. We're gonna go with D, okay? I'm gonna make it a little tough on you, Aaron. I know how easy this is so far for you. So if we take that form, right? Spring form, stiffness times deflection equals force. Well, now we have this stiffness times deflection equals force up there with respect to our element, right? If we pulled out some of our constants, right? AE over L, it's out in front. Any ideas of what we would put in the top row of that K? 1, negative 1. Right, and then we get our F1 and F2. So if that's the case, we know that one's negative the other. So we get negative 1 and 1. So we get this nice matrix-based form of our stiffness of our element. Right? One linear element sitting in space. Right? Cross-sectional area of A, length L, modulus elasticity E, okay? And it has 2 degrees of freedom. We can just push the first node in one direction in the axial direction of the bar, and the second node we can do the same thing. Okay? This K matrix, okay, in finite element terminology, what we would call the characteristic matrix, all right? It's the characteristic matrix because not everyone is interested in structural engineering, right? So sometimes this might be characteristic of the, say, thermal properties of a material, okay? Something other than stiffness. But for us, which for, whoops, lost it there, which for structural problems this is the stiffness matrix. As mentioned, right? Equation 3 there is really just the equation for a linear spring. Right? And something to think about, right? Really, thinking about all structures as a system of linear springs isn't a bad approach, okay? Right? Stiffness attracts loads and mechanics of materials, right? Everything has a stiffness. It might just not be a axial stiffness, it might be a bending stiffness, it might be a torsional stiffness, rotational stiffness, right? But everything has a stiffness associated with it. That stiffness, driven by displacement, gives you force, right? So thinking of all structures, especially when you're modeling, we'll talk about that later on, but when you're modeling things, it's always good to think of them with respect to stiffness, right? And in your model, it's driven by stiffness. So if things aren't looking right, or the behavior or displaced shape that you're looking at doesn't seem right, right? Think of it from a stiffness perspective and where loading might be going. Example of this, a lot of times when you model buildings, Cobley Hall or something like that, or like we were modeling Norm, what's a good one? On campus would be like Rendezvous Dining Pavilion, okay? So I model it, it's got a concrete diaphragm on the second floor, concrete diaphragm on the first floor, it's an entire first, like a full basement underneath it, okay? And so lateral elements, sometimes, depending on where, I mean, they could be continuous from the roof to the ground basement level, right, on the very, very bottom, okay? But the stiffness of the diaphragm can sometimes dominate so much so that it actually is pulling load out of a brace frame and putting it into another one. Because it is stiffer than the brace supporting that brace frame below itself. So like we were modeling, it was either Rendezvous Dining Pavilion or some other building, and it was just making no sense that if we were getting like the reactions to design like an ordinary brace frame, right, and our brace forces at the main floor level of the dining hall were more than at the ground level in the basement of the dining hall. And after looking at it and thinking of it from a stiffness perspective, we had this huge, massive diaphragm that was supported, right, this big deep beam that's supported by 10-inch thick concrete walls on the entire, all perimeter of the building. And that was way stiffer than this brace frame that was extending below the brace frame that went from roof level to basement level, right? Just kind of a weird phenomenon that happens, but it's all based on stiffness, okay? So it took us a while. That was a 2 or 3 day little endeavor, racking our brains about it. Was that right? I have no idea, okay? And I couldn't tell you with ultimate certainty that that is right, but none of you could either, okay? But I'll tell you, I spent a lot of time modeling that building, and I feel pretty good about it, okay? So we can do the equilibrium approach, Okay? Very straightforward, obviously, for a linear element, axial element. Another approach that we can use is called the vector approach, which we would call, well, did I write that down? I didn't. For this one, we would say this is a free body diagram at our nodes. The vector approach, okay, is a unit degree of freedom approach. What do we do? Well, we create a stiffness matrix, recognizing that each column in our K matrix is the vector of forces that produces a unit value of degree of freedom in question and 0 for each other degree of freedom. So for each column of K, right, it's the vector of forces. So really, if we looked at our K, this is force 1 and force 2, right? That's each row. That provides a unit deformation of our degree of freedom for each of the columns. So our first column really gives us a vector of forces that produces a unit degree of freedom displacement at use of 1, right, and 0 at use of 2. And then similarly, if we look at the second column, U2, same thing, right? It's the forces at 1 and 2 that give us a unit displacement at 2. Make sense? So if we start with that approach, right, A being our first column, we're going to say that the displacement at use of 1 is 1, and the displacement at use of 2 is 0. If we drew a free body diagram of that, right, we'd essentially say that we're going to fix U2 and allow U1 to move over a unit displacement. What's the displacement of an axially loaded bar?
Why is A and B the same displacements?
What's that?
Am I just messing?
What do you-
U1 equals 1, U2 equals 0 at A, and then for part B, you said U1 equals 1 and U2 equals 0.
Oh, shit. I got up too early and I was here on time. Okay? That's my excuse. Is that okay? I make the rules, all right? I used to not be able to make the rules. Now I can make the rules. I'm going to make the rules. All right, what's the displacement of the axially loaded bar? Just gave this to my sophomore class. It's the equation. Fucking crushed it. Way to go. So PL over AE, well, in this case, we have force instead of P. It's F1, L. Screw AE, I'm doing EA. Okay? That's way better. Isn't that way better?
I guess if it's F, then it's fleet.
It's F. F1 L over EA equals 1. Well, based on this, if we rearrange this, F1 becomes EA over L, right? We know from an overall free body diagram that F2 is negative F1. Well, that means that F2 equals negative EA over L. What does that mean up here? Well, that means F1, in order to get a unit displacement at 1, right, and 0 at 2, our forces would be EA over L and negative EA over L. Right? Similarly, now we have F2 L over EA. F2 is EA over L, and F1 we know is negative EA over L. Beautiful, negative EA over L and EA over L. If we pulled our constants out, EA over L, right? Yay. Our K matrix, right, matches what we found before. which is good. So we can do this the same way, right? Two different ones. Equilibrium attached to each one of the nodes, or we can step back and use our vector, right, degree of freedom approach, right, vector approach, unit degree of freedom, and come up with the same answer. Well, in the real world, right, keep talking about the real world when we're sitting here in academia, right? We normally don't have just one bar element, right? Or one beam element, or one plate, right? So often not interested in just one bar. We want a series of bars. Well, the second approach we took, right, the vector approach, is going to work very well for several elements. We could do the equilibrium approach too, with respect to a linear bar, but it starts getting very complicated quickly with other elements. So the vector approach, if we think of every column in our stiffness matrix, right, is the vector of forces that create a unit displacement at that location, right, at that degree of freedom, and then 0 everywhere else. So we go through the same approach, right, with 2 bars. If we had 2 bar elements, 1 and 2, which means we have nodes 1, 2, and 3 now. Each of those bars has a stiffness, right, K1 and K2, and a length L1 and L2. Our form, we know, right, is our spring, little d, little f. Because it's my world, you guys are living in it, right? Little d, little f. And we know that each one of our columns is a vector of forces, right? F1, F2, F3, or forces at our degrees of freedom that give a unit displacement of our degree of freedom, right? And 0 everywhere else. So we go through the same exercise, right? In this case, I'm going to change that to black. Say we have F1. We're going to have F2. Because we have to have 0 displacement, right? If we get a unit displacement at 1, we can't allow either of these nodes to displace. Well, that means that the third node doesn't displace, right? Which means there's 0 force at the third node. So we get 0. So that would be this guy here. Same approach, right? FL over EA. F1 now equals A1, E1 over L1. We're going to call that just K1. That's our stiffness K1. Overall free body diagram, we get F1 equals negative F2, right? It has to resist that force at 1. So F2 is negative K1. So F1's K1, F2 is negative, so we get K1, negative K1. Do the same approach with U2.
Scroll just for a sec.
Man, you guys are asking a lot. Is that Sutton?
That was me.
Oh, man. Whew. You guys lucked out.
I was trying to understand why there's no force at node 3.
Because this is a vector of forces, right, that imposes a unit displacement at U1. So if we were to take this series of 2 elements, 3 nodes, and we let the first node displace 1 unit, and we say the other nodes can't displace at all.
Oh,
So that means that this bar essentially doesn't change any length.
so it's almost like okay.
And if there's no change in length of this bar, then that means there's no force at that node, right?
Sure.
So that was U2 or U1 equal to 1, U2 equal to 1. Well, now we're going to be pulling, right, our first rod, and essentially pushing our second rod, and we're gonna impose a unit deformation, right? So both rods see a unit deformation, which means we're gonna be pulling, or F1 might be acting to the left, right? F2, in order to get that unit deformation, needs to be to the right. And then F3, there you go, Elias, there's your F3, buddy. F3 needs to be there as well. Now, if we look at 1, right, the deformation at node 1, well, we know that it equals to 0. Well, that also equals F2, L2 over A2, E2, F2, L1 over A1, E1, right? Right, deformation is equal to the force times each of those rods, right? Because now we have 2 rods as part of that. So if we rearrange this, we pull F2, right? We really want a vector of forces. So we have L2, A2, E2, L1, A1, E1. Rearranging for the vector, right? Or the force, really. So we can create this vector. L1 plus E2, A2, L2. We're going to say that that is really equal to K1. And the second term in there is K2, right? E2, A2 over L2. Therefore, F1 equals negative K1 and F3 equals negative K2, right? If you did the same thing and said we need to resist that force in each one of those rods, if it displaces 1 unit out to the side, you could say that that unit displacement is now equal to F1 times A over, or L over AE. So what do we get? Well, now our vector of forces, we have F1 equals to negative K1, F2 is K1 plus K2, and F3 is negative K2. So we get negative K1, K1 plus K2, and we get negative K2. Lastly, vector approach, right? We impose a unit deformation at U3 now. Well, Elias, you get to lose F1, sorry. But we do have forces now at F2 and F3. Same derivation, we end up with F3 equals K2, F2 equals negative K2, and F1 equals 0. 0, negative K2, K2. This is U1, U2, U3. This is F1, F2, and F3. Any questions on how that derivation went? This is as simple as it gets, okay? I'm a simple guy. All right.
Go back down.
Sure can. All right. Well, alternatively to even this approach, as you guys probably have done in the past, whether it's in advanced mechanics and materials, in structures 1, right? You did some of this matrix type stuff in structures 1, right? Or Ladine's class, right? We can essentially just add up, okay, or assemble, what we call assemble, all of our stiffness matrices for each of our elements into one global stiffness matrix just by adding them in, right? We could just add the element stiffness matrices together. So if we start out with knowing that K1 is A1, E1 over L, right? That's our stiffness. Take that times the displacement of that first bar, and we're going to get our force. Same with K2, right? Instead, it's going to be A2, E2 over L2. This is L1. So if we looked at element 1, right, from up above, we've got this stiffness matrix, K1, minus K1, minus K1, K1. And each one of these, right, is U1, is a vector of forces that creates a unit displacement at that location, right, at that node, and 0 elsewhere. Same with K2. Well, now we've got K2 minus K2 minus K2 and K2. And again, we've got our displacements associated with that. U1, U2, F1, F2.
Would that be like U2, U3?
Oh yeah, it is. Sorry. You're so right.
And then F2, F3?
Yep. Sure is. Sure is. So we start with an empty structure-sized stiffness matrix. What's structure size mean? Well, it just means it's the size of our degrees of freedom by degrees of freedom. In this case, right, we have U1, U2, and U3. Those are our degrees of freedom. So we get a appropriately sized, structure-sized stiffness matrix. We can merely add in our element 1 with respect to our U1, U2, right? Zeros elsewhere. We have no other contributions. Then we can finally add in element 2. Right, so we've already have K1 minus K1 minus K1, K1. Now we need to add in K2 minus K2 minus K2 and K2. This process is called assembly, as I mentioned. Right, we got the exact same answer. And this process is the exact same, right? As I said, we start out with this appropriately, like a structured size stiffness matrix, which is your degrees of freedom by degree of freedom. So this is the exact same regardless of the number of degrees of freedom included. Right? If we had 2 degrees of freedom of each end of the bar, right, then this would be a 6 by 6 matrix, right? It's the same regardless of the types of elements included. And it's regardless of the way the elements are formulated also.
What do you mean by types of elements included?
Right, so if we had, you could have 2 different elements, right, connected at a node, right? They only know each other at the node. And that element might have different degrees of freedom, potentially, which would just add to the overall structure's degree of freedom, which would add to the size of this stiffness matrix. And you would essentially take the stiffness matrix, right? It might not be a linear bar, right? It might vary non-linearly, right? And so this matrix for, say, one element is going to be different than the second element, but you can still add them together in assembly, right? So like one element is only going to be a function of U1 and U2. The other element is going to be a function of U2 and U3. But at the common node, right, the stiffnesses of both of them are going to interact. They're going to contribute together. But you can still use the same process of assembly, of essentially just adding in one stiffness matrix for the first element and adding on top of it the second. Does that make sense?
Regardless if it's like a 1 degree freedom element? Or
No, so then that's where,
like types of elements, like a different type of
Yes.
element than this would be like.
but the degrees of freedom need to match at that nodal location.
Right.
So it would essentially be that you have a linear bar element to a nonlinear bar element, right? All that's saying is that that nonlinear bar element has a different assumption based on the displacement of that node versus the linear bar element, right? We used Hooke's law for our constitutive relationship. It might not use Hooke's law. It might use some other type of constitutive relationship. But you can still add them together because the stiffness at that common node is going to be like working with respect to both of those elements, right? You move that node and that first nonlinear element is going to be affecting the linear element and vice versa. Does that make sense? That's why it doesn't matter either which with respect to the way the elements are assembled or are formulated, right? But the degrees of freedom need to be the same. All right. We are getting closer to something real, right? So closer to one other step we need to make to get closer to something real is the real world doesn't have all these line elements in a line, right? Things are in different orientations. And so even though locally, right, the stiffness of this bar element is a function of the direction along the length of the bar element, this bar element may have a kink in it, right? It could be straight and then be up, right? A truss is a good example of that. Right, where we have all these laces and cords acting together, and the local direction, right, the direction along the length of our bar element doesn't coincide with, a lot of times, a lot of the other elements in the system. And so we need to figure out a way to relate element orientation. Right? So real world's not a straight line. Right, and this is our work till now. Everything was very simple. Everything was in line with each other. So we need a way to relate local element orientation to a common orientation, or what we would call, right, this would be with respect to global orientation. So we need to consider our bar element kind of stuck out in this global or common coordinate system, and it has its own local coordinate system at the same time, right? So if we had some sort of X and Y global coordinate system, and our local bar is oriented, right, or rotated with respect to one of the axes, we might devise a diagram something like this, right, where we have X prime and Y prime, which are the local coordinates for this bar element. We have some sort of angle with respect to our X, our global or our common coordinate system. We still have our forces at 1 and 2. We still have our deformations, right? Our degrees of freedom at our node 1 and 2. So I stole a little bit out of Cook because I didn't want to draw all this up. Oh. Oh, I was going to after I talked about this, but I'll give it to you now. All right, we're going from KD prime, F prime, to KD F, right? Essentially just saying we're going from our stiffness equation with respect to local coordinates to our stiffness with respect to a common or global coordinate system, okay? So we have figure A here, right? If we look at our, this would be our local behavior that's going on. Our local displacements is our U1, U2 primes. our local forces are F1 and F2, right? The axial forces in our bar. If we were to translate that to a global or a common coordinate system, right? We're gonna have components, right, of each of those forces and deformations with respect to now this common coordinate system, right? So now F2 becomes Fx2 and Fy2. Our deformation at 2, U2, right, becomes some sort of new, or U2 prime becomes now a U2 and a V2, right? Coordinates in each of those directions. So our D matrices, D prime matrices goes from just U1 prime and U2 prime to U1, V1, U2, V2, right? So this would be our global. So based on geometry, right, we can make a relationship of U1 and V1 to U1 prime, right? Same with F1 to Fx1 and Fy1, right? Our global coordinate systems. Just based on the geometry, essentially coming up with our components based on beta, or that orientation angle. So if we look at D prime, and we're going to relate our local deformation, right, U prime, we would get this equation that they show up there as U cosine of beta plus V sine of beta. And if we take each of those and we put that into matrix form with respect to U1 prime and U2 prime, right? Each one of those is going to have a U cosine and a B sine. We could say that D prime with respect to U1 prime and U2 prime equals cosine of beta sine of beta and this is what we would call our transformation matrix times our common or global, right, displacements, U1 and V1, U2 and V2. Multiply all of those out, we would get our, right, D prime is our transformation matrix times our displacement matrix in the common global coordinates. Obviously, we need to take and relate our local forces, right? The forces along the axis of our linear bar to the forces in the components in the global sense. Similarly, from figure B, we get this F1 sine beta, that's our component, and F1 cosine beta.
F1 or F prime?
Or F prime, sorry. Because we're going from our local F prime to our global Fx next Fy. Or if we broke it down further, right? Each one of those with respect to our node 1 and node 2, we would get these matrix development. This is our transformation matrix transposed, right? In order to get our global or common. So we end up with this relationship between forces, our local forces, and our common or global forces based on this transformation matrix. Well, in the spirit of being on time, I'm going to let you go at 9:50. Does that sound?
Spirited.
Huh?
sounds spirited.